Hi and welcome to today's video. In this video, we're going to be concerned with the inverse of a matrix. Now, in the last videos, we were talking about matrix multiplication. And of course, if you compare that to multiplication in the real numbers, there's a lot of differences there already. But of course, there are also things that these two operations have in common. So, one possible question to ask is there also something like matrix division? And division in the real numbers basically means you have an inverse operation to multiplication. So there's this neutral element, 1 in case of multiplication. And for every possible real number, with the sole exception of 0, there is an inverse number such that the number multiplied by its inverse yields 1, the neutral element. For matrix multiplication, we have seen there is also a neutral element, the identity matrix. So it's a natural question to ask, is there also something like the inverse element? And this is a question that we're going to investigate and answer in today's video. So this section is titled The Inverse of a Matrix. And the goal today is to see if there's an inverse matrix multiplication operation. So we want to reverse matrix multiplication in the same way as we can reverse multiplication for the reals. And I already said for the real numbers, we have something like for an element A, there is always an element B, such that A times B is 1, with the exception of 0. And 1 is the neutral element of multiplication. And this element B is what we call the inverse of A. And we write it as A to the minus 1. So this exists for A not equal to 0. And for matrix multiplication, we also have a neutral element, that is the identity matrix. So IN for a matrix of size n. So an inverse element would have to satisfy basically the same equation as for the reals. So the inverse for a matrix A has to satisfy A times B equals IN. And because matrix multiplication is not necessarily commutative, we also have to have the reverse of that, B times A equals IN. Of course, we want both relations to be true in the case of an inverse. So that already gives us one restriction for the inverse. With this equation to satisfy, the only possible matrices that can be considered are square matrices. Otherwise, we can never get IN that way. So A must be a square matrix. And that motivates the following definition of an inverse matrix. So let's say we have a matrix A. Let A be an n by n matrix, so a quadratic matrix. Then let's first define the inverse if it exists. And we say that A is called invertible or you will also say regular, or possibly we'll also say non-singular. So all of these names are common. And a matrix is called invertible if there is an inverse, that is a B that satisfies the equations above. So if there is a matrix B that is then also in R to the n by n, and that satisfies A times B equals B times A equals In. And if such an inverse exists, then we will denote it by A to the minus 1. So if A is invertible, its inverse is denoted by A to the minus 1. And second part of the definition, that's just another term. If a matrix cannot be inverted, so if it does not have an inverse, then we will call it not invertible or singular or non-regular. So a matrix that does not have an inverse is called either non-invertible or singular or possibly non-regular. Now, of course, a good question to ask here is, are they even matrices that have an inverse? Or are we talking about the empty set here? And if there are matrices that can be inverted, can every matrix be inverted? And if not, what are criteria? How can I know whether a matrix can be inverted? Is there more than one inverse? And how do we compute an inverse? Of course, we want to know that as well. We'll answer all of these questions in turn. Let's first look at a simple example that will show us that there actually is such a thing as an inverse, at least for some matrices. So we'll have a look at the matrix A, 1, 2, 2, 3. And I claim that the matrix B, that looks like this, minus 3, 2, 2, minus 1. I claim that this is actually an inverse of A. And we're going to verify this by computing AB and BA. So A times B, that is 1, 2, 2, 3 times minus 3, 2, 2, minus 1. So what do we get here? We'll start with the first row here and the first column here. And we get minus 3 plus 4. Then let's do the second row and the first column. And we get minus 6 plus 6. Then here's first row, second column. That is 2 minus 2. And finally, second row, second column. That is 4 minus 3. And as you can see, this is actually this matrix here. So we do get the identity matrix I2. That's a good start. So AB works. What about BA? Now BA, that is minus 3, 2, 2 minus 1. That's the matrix B times A. A is 1, 2, 2, 3. And again, let's do the computations. First row, first column. That is minus 3 plus 4 again. Second row, first column. 2 minus 2. Then we get first row, second column, minus 6 plus 6. And finally, second row, second column, that is 4 minus 3. So again, we get the identity matrix I2. So what we can see here is indeed A is invertible. With inverse matrix A to the minus 1 is the matrix B. And of course you will notice this relation here is symmetrical. So if A is invertible with inverse matrix B, then of course B is also invertible with inverse matrix A. Yeah, for B, the same two equations hold. Just the order is reversed here. So let's write down that as well. And B is also invertible with B to the minus 1 being A. Okay, so that settles one of our questions. Is there such a thing as an invertible matrix? Yes, there is. Here's an example, and it's not just a trivial one. Let's have a look at another example, and that'll settle the second question that we've asked. Let's say we're looking at this matrix here, 1, 0, 0, 0. Is that an invertible matrix? And it will turn out it's not. So there are also matrices other than just the 0 matrix that cannot be inverted. And we can see this in the following way. So question is A invertible? Now let's assume that will be the case. Now, if A is invertible, then let's say then there's an inverse, and let's say we name that inverse B. So B is its inverse, and B is a 2 by 2 matrix, and let's say it has the elements B11, B21, B12, and B22. So let B be its inverse. Then we know that I2 is A times B. And we can compute A times B, actually. So we have the matrix A, and we have the matrix B. So let's just do the computations. And we can see, well, again, let's do first row, first column. That's B1. 1 like this. Then we do second row, first column, that is 0. Next, let's do first row, second column, that's B12. And finally, second row, second column, that is 0 once again. And if that is to be the identity matrix, like this, then surely you'll be able to see there's a 0 here and a 1 here. So there's absolutely no way this could ever happen. Here's a contradiction. So this matrix here, what we got from the matrix multiplication, that can never be equal to I2. And that means A cannot be inverted. So A is non-invertible. So there are both kinds of matrices. There are invertible matrices and there are non-invertible matrices. One other question that we didn't answer yet is, if there is an invertible matrix, is it uniquely determined? Or may there be more than one, possibly different inverse matrix? And that's the last question that we'll be discussing today in this video here. And there's a simple theorem that settles that question. Of course, I'll also show you why that theorem settles the question. That theorem states the uniqueness of the inverse. And what it states is, let A be an invertible matrix. So A is an n by n matrix. And then let B and C be matrices that satisfy the necessary equations. So B and C be matrices in R to the n by n. With, on the one hand, we want AB equals BA equals IN. And on the other hand, we want AC equals CA equals IN. So both satisfy the equations for an inverse matrix. And the claim is, then B must be equal to C. So there are no two different inverse matrices. And B is equal to C. And that means the inverse of A is uniquely determined if it exists. And I'll show you the proof because that's sweet and simple. The idea is a pretty simple but compelling one. Let's start with the matrix B and let's rewrite B. And we rewrite that by multiplying it with the neutral element of matrix multiplication. So instead of B, we can write identity matrix times B. And now we know that the identity matrix can also be written as C times A, like this here. So we'll do just that. We'll write C times A instead of the identity matrix. And then, using the rules of matrix multiplication, remember matrix multiplication is associative, so it doesn't matter whether we first compute C times A and then times B, or we first compute A times B and then multiply C times that result. Same thing. Now A times B, on the other hand, is also the identity matrix. So what we get here is C times the identity matrix. Well, of course, C times the identity matrix is C. So what we have here altogether is B equals C. And that's exactly what we were to prove, because that is the statement of a theorem. So if an inverse matrix does exist, then it is uniquely determined. That's what this theorem here tells us. And of course, the next question to ask is, how do we determine such a matrix? And how do we find out if one exists or not? Are there simple criteria? Is there an algorithm, something like Gaussian elimination? Can I use that for matrix inversion or something similar? And we are about to find that out. But before we do so, we'll quickly summarize a few key results, a few key properties of matrix inversion, so that the following computations will become a little easier for us. That's going to be in the following videos, so I'm sure I'll be seeing you then.